back to where we were. So, random error, randomly distributed variation. Bias is systematic error where there's something that's affecting everybody in the group and making you get an answer that's different from the truth. We can divide bias, or we can classify it into different types of bias based on the reason for the error. It's all bias. It's all making you get an answer that's different from the real answer. But we can call it different things based on what's causing the bias. So, selection bias. What does the word selection mean to any of you? We're selecting something. What are we doing? We're choosing something. Selection bias usually refers to when you're selecting your sample. So we talk about selection bias when we're talking about if there's systematically something from your sample. So if your sample is not the same as the population that you're talking about, so let's say we're interested in the general population of students at SLU, but we only sample the nursing school. Do you think the students in the nursing school are entirely representative of the SLU undergraduate student body? No. So when we're talking about being able to generalize back, we have a systematic bias towards the nursing students, and their responses might be indicative of the truth for the nursing students, but they're not indicative of the truth for the entire population. Let's see. So, selection bias occurs whenever your investigator selects your source population or determines your eligibility criteria. So eligibility criteria is how you get in the study, right? If you determine your eligibility criteria, sorry, I lost my place. So it occurs when you're selecting your study sample, your study population, or when you're selecting your eligibility criteria for who's going to get included in your study. That's when it occurs, sorry. So it can affect the internal validity of your study, so it can affect if you get the right answer in your study. That's the internal validity. Does your study come to the correct conclusion? But it can also affect the generalizability. That was the nursing example, right? When your study sample is not representative of the larger population. It's due to systematic differences. So remember, bias is always a systematic difference. It's a systematic error in the characteristics between those who get included in the study and those who do not. There's two main types. There's a couple of other ones, but the two main types that we really concern ourselves with are exclusion bias and Bergson's bias. So exclusion bias happens when the investigators apply different eligibility criteria to the cases and the controls. So for example, if we're doing a study on, we're conducting a study of drug abuse cases in the emergency room. So our cases are people that come in that are intoxicated or under the influence of drugs, and we get them all from the emergency room. But then we go to choose our controls, and we just do a random digit dial phone interview to find our controls. The people that end up in the emergency room, choosing our cases from the emergency room, and then our controls from just randomly whoever picks up the phone, is probably going to systematically influence our results, because the people who end up in the emergency room usually are sicker, lower socioeconomic status, have other issues going on. They're not necessarily representative of the people that have houses with telephones. Right? Especially because when you're talking about emergency room populations, you also end up with a lot of people that are homeless, which is also, right? So and homeless people don't usually have home telephones to call. So none of those people would ever be able to end up in your control. So there's a systematic difference. Your source population for your controls was not the same as the source population for your cases because of the way you chose your controls. And that's exclusion bias. Bergson's bias refers to a specific mathematic phenomenon that only appears when you're talking about hospital admission rates, or admission rates to anything, but we typically refer to it as hospital admission rates. So hospitalization rates for people with your disease of interest are going to differ, or it's possible that those rates differ from whatever control condition you're using. So if you're using hospitalized cases and controls, but your hospitalized cases are patients with diabetes and your hospitalized controls are people that broke their leg, it's great that they're all in the hospital, but the admission rate for the people that have diabetes is probably going to be different from the admission rate of the people that have that broke their leg, right? That's Bergson's bias. Now, that doesn't mean that you can't do a study where you use people with condition A from the hospital and compare them to people with condition B from the hospital. You just need to be careful about the underlying rates of people that are entering the hospital with that condition. You need to be aware of that. Selection bias is the most difficult bias to grasp, the most difficult kind of concept. So sit on it, we can come back to it if it's still kind of confusing. Information bias, I think, is a little bit more intuitive when you're talking about understanding it, at least. So information bias happens when there's some kind of flawed component in measuring your exposure or your outcome. And this leads to inaccurate classification. So general misclassification bias occurs when you mistakenly put people that should be classified as cases in the control and classify them as controls, or people that should really be controls but you accidentally call them cases. You have misclassified them, you have put them in the wrong category. You can also call it misclassification instead of talking about cases and controls if you're talking about exposure and unexposed. So you can misclassify someone as exposed when they really didn't have the exposure, or you would misclassify someone as unexposed even though they really did have the exposure. Recall bias refers to differential recall between cases and controls. So a lot of time, cases are more likely to remember every single little bitty tiny thing that could have been exposure than controls, right? So if you have just had a premature baby, you are probably going to be very cognizant of every single little thing that happened during the course of your pregnancy, right? But if you gave birth to a normal baby and you're using those people as the controls, looking for exposures, people who gave birth to a normal baby that wasn't premature probably don't have the same sensitivity and aren't asking themselves, what did I do? What did I do? What happened? And they may not remember every single little thing. So they may not recall an exposure that they had just because they're not looking as hard for it. So it's a differential recall between the cases and the controls. Let's see. Reporting bias happens when a larger percentage of either the cases or the control subjects are reluctant to report the exposure. So this happens, sometimes it's called social desirability bias. It's fairly common when you're talking about sensitive topics like drug use, sexual behaviors, things that people don't really want to talk about, things that people might be embarrassed about. So a lot of times you might have cases or controls that are more or less likely to report things that have happened in the past. Yeah.
What else did you say it was called?
Social desirability bias.
Okay.
Yeah, so you're not telling the truth because you're embarrassed about the answer or because you're trying to please the person that's taking the measurement. So people that are trying to give the right answer instead of giving the actual answer. And surveillance bias occurs when a disease may be better ascertained in a monitored population compared to the general population. So, for example, airline pilots undergo frequent and intensive routine testing, right? Routine medical examinations in order to keep their pilot's license. In order to be able to fly, you have to see the doctor a lot to make sure that you are in good health. So there are a lot of conditions where pilots they look like they have a higher prevalence of certain conditions, but it's not because pilots actually do have a higher prevalence, it's because we're looking for it in them. So the general population isn't necessarily screened all the time, but pilots get screened every single year. And so it looks like there's more people with the disease when in fact it's just because we're screening them more often. Surveillance bias, you can also think, another example, so you can also consider surveillance bias sometimes when the definition of something changes. And so when a definition of a disease state changes, and then all of a sudden it appears like there's a huge increase in people that have the disease, but it's not really because the true baseline of people that have disease is because we now are classifying something else as also having that disease. Or like autism rates have been increasing, and there's evidence that they really are increasing, but part of the reason autism rates seem to be increasing is because there's a better acknowledgement in society that's a problem, and so more doctors are diagnosing it because they're looking for it. That doesn't mean that necessarily the baseline rate of autism is changing, although there is evidence that that's happening. But some of it is just due to the fact that people are more cognizant that it's there, and so they're more likely to diagnose it. That's surveillance bias. All right. A little bit more about misclassification. We can classify misclassification into two categories: non-differential and differential. Non-differential misclassification is really kind of akin to random error. This happens so you've accidentally misclassified a case as a control, or a control as a case, or is it exposed as an unexposed, but it's kind of randomly distributed and evened out, and there's no systematic reason this is happening, it's just a little mistake here or there. That creates extra noise in your data, but it probably won't affect your actual answer. It'll bias your results so that your effect size looks smaller. But besides that, it's not gonna make you come up with the complete wrong answer. It's not a systematic bias. Differential misclassification occurs when the misclassification is not random. So the rate of misclassification is either higher in the controls or higher in the cases. Higher in the exposed or higher in the unexposed. Differential misclassification is bad, bad, bad. This is the bias that we're talking about. So all of these other biases that we talk about when we talk about selection bias, when we talk about recall bias, all of those biases lead to differential misclassification, right? Misclassification is simply referring to putting people in the wrong category. What matters is are people randomly ending up in the wrong category, or are people systematically ending up in the wrong category? Depending on who gets misclassified as who in differential, you may end up with an effect size that's much larger than you expected, or it might bias it towards the null and you may end up with an effect size that's smaller. You can't really tell. That's why this is so dangerous. You can't really correct for it once it's a problem. All right. This leads us to confounding. We've kind of brushed on the idea of confounding a couple of times. But confounding simply means that it occurs, you have two variables that you think are related to each other. But then when you take into account the third variable, that relationship changes or disappears. So you see your relationship between x and y, you do an odds ratio, you calculate an odds ratio and you see this relationship. But then you take into account variable z, and then all of a sudden the relationship between x and y isn't there anymore. Or it's a lot smaller than it was before. So, for example, there is a very, very strong association between alcohol use and lung cancer. Does that mean alcohol use causes lung cancer? Why might there be what might explain that relationship?
When people drink, they smoke.
When people drink, they smoke. And we know there is a very strong causal relationship between smoking and lung cancer. So here, alcohol use would be X, lung cancer is Y. There's a strong association when we look at it that all of that's explained because of smoking. Smoking is the confounder in the relationship between alcohol use and lung cancer. So, in order for a variable to truly be considered a confounder, it has to meet three criteria. First, the confounder must be associated with the exposure. So smoking and alcohol use tend to happen together, they are associated with each other. The confounder must be associated with the outcome. Smoking and lung cancer are associated with each other, right? And finally, the confounder must be an independent risk factor for that outcome, meaning it can't be in the causal pathway. So what does a causal pathway mean? It means that it can't be so like, if you take Lipitor, it lowers your cholesterol level. You're less likely to have a heart attack. So lower cholesterol levels cannot be a confounder in the relationship between taking Lipitor and having fewer heart attacks, because it's in the causal pathway. So Lipitor causes lower HDL, or lower cholesterol, which causes fewer heart attacks, right? Does that make sense? What a causal pathway is?
Can you repeat that last like step for it to be a confounder?
So for it to be a confounder, it cannot be in the causal pathway between, so when we had X and Y, right?
Yeah.
It can't be between X and Y
Okay.
to correlate. It can't be a step on the way. Alright, oh, and then this is just a diagram of, I use Lipitor, but this uses exercise, same idea. Lower HDL can't be a confounder in the relationship between exercise and myocardial infarctions or heart attacks, because it's in the causal pathway. Exercise causes lower HDL, which causes fewer heart attacks, or causes you to not have a heart attack. Does that make sense? You look like it doesn't make sense.
No, it does.
You sure?
Yeah.
It's okay if it doesn't, we can talk about it again.
No, it does.
Okay. Well, we can always revert back.
I lot, I guess.
We can always revert back. Alright, I think a lot of this becomes clearer when we walk through an example. I don't know why I picked this little like microphone thing, but anyway. So we're listening to the news, and you hear this nice little news lady say, the observational study showed that teenage girls who watched R-rated movies were more likely to become pregnant. In fact, they were 15 times more likely to become pregnant than teenage girls who did not watch R-rated movies. So based on that statement, she said, we've done an observational study, and we found that teenage girls who watch R-rated movies are 15 times more likely to become pregnant. Based on that statement, what is our exposure?
Having seen R-rated movies.
Yes, R-rated movies are our exposure. So what's our outcome?
Pregnancy.
Yes, teen pregnancy. So, what is the relative risk of the association between R-rated movies and teen pregnancy? 15, yeah. So that's an association. That's a real, I mean, well, this is a made-up example, but that's like the real association, right? That association exists. Then the question becomes, is that association causal? Does watching R-rated movies cause teenage girls to get pregnant? Probably not. But let's walk through. Let's see. So the first thing we do when we're looking to assess confounding, we start with our first measure of association. We start with our 2x2 table. So we have our disease state, in this case, teen pregnancy, our outcome, and R-rated movie watching. So we don't know, I haven't given you the numbers, but we do know that the relative risk, if we were to work it out from the numbers, the theoretical numbers from that table, that girls who watch R-rated movies are 15 times more likely to get pregnant. So, now the anchor woman starts quoting the investigators. And she says, the study establishes a clear progression that begins with watching R-rated movies and leads to teenage pregnancy. She goes on to say, if we keep our teenagers from watching R-rated movies, we can go a long way towards preventing teen pregnancy. Now, on the basis of this information, on the basis of what we know there's an association between R-rated movies and teen pregnancy. Do you think that this is a legitimate statement that you can make based on the information that we have today? Why not? I mean, wouldn't it be easy? We just kept all the teenage girls from watching R-rated movies. We'd have completely abolished the problem of teen pregnancy. Why don't we think that her statement is a causal statement? She is saying, you watch R-rated movies, you get pregnant. Yeah.
There can be like a lot of confounding variables there. Maybe like the parents don't watch over their kids as much, so they watch R-rated movies, and that leads to them not being watched as much, maybe being home alone more, and that could lead to it, and stuff like that.
Exactly. There's a whole lot of other factors that could be going in there, which I should just, this is what happens when I borrow slides from people. Thanks. And they go back to all the like little flippy things. Anyway. So we blamed R-rated movie watching, we blamed teen pregnancy on R-rated movie watching, but you're right, there's probably a lot of other things that go in. Girls that watch R-rated movies, there's probably a lot of other factors that are going on. And by the way, we are not blaming teenage girls for getting pregnant, all the little teenage boys are just as equally responsible. Sorry, this is one of my like little pet peeves, when we always blame the girls for getting in trouble, when it's not their fault, because they did not get in trouble by themselves, now did they? Alright, but what we cannot say based on what we know is that watching R-rated movies causes teen pregnancy. Exactly because you said there's reasons that there might be. So the girls and their little boyfriends might not be supervised as often. So they have more opportunities to. They may not have parents who decide that they don't need to talk to their children about preventing pregnancy. Lots of things that could be going on. Alright, so that is what we're talking about when we talk about confounders. Yeah, there we go. So lack of adequate supervision might be a confounder in this relationship. But remember, there's 3 criteria for something to be a current. It has to be associated with the exposure, it has to be associated with the outcome, and it cannot be in the causal pathway. So, you think lack of adequate supervision might be associated with girls watching R-rated movies? Probably. That it's associated with teenage pregnancy. So, it's associated with the outcome, it's associated with the effect, and lack of adequate supervision isn't a step in the pathway between watching R-rated movies and teenage pregnancy, right? So we've met those criteria. But now we have to determine statistically if something is a confounder. We're going to use a different example for that. Alright, let's go back to our smoking and lung cancer example. Our drinking and lung cancer example. So, we have done a cohort study looking at heavy drinkers and the development of lung cancer. And in this particular case, we managed to do a prospective cohort study with a fixed cohort for simplicity of the analysis. We know everybody in our sample, and we have 33 people that were heavy drinkers that developed lung cancer, and 1,667 who were heavy drinkers that did not develop lung cancer, so on and so forth. Go ahead and calculate the incidence rate, or the relative risk, sorry. Go ahead and calculate the relative risk of lung cancer. I remember how to do this? Yes? So incidence rate in the exposed over incidence rate in the unexposed. Sorry, cumulative incidence. Probably be more precise when I talk about these terms. Alright. So how do we get incidence in the exposed? What is it? Somebody anyway? Anybody?
33 divided by 1700.
Yes, 33 divided by 1700. So, in the exposed, it's everyone in the exposed that developed the disease, divided by everybody that was exposed. So the incidence rate in the non-exposed, everybody that developed the disease in the unexposed, divided by everybody in the unexposed, right? So what did you get for the relative risk? Did anyone actually do it?
I got 1%. Yeah. 0.011 for non-drinker.
Oh, go ahead and calculate the full relative risk. Yeah, sorry.
1.65.
Yes, 1.65. Sorry, I don't have the incidence ones written down, so I don't actually know if that's right or not. Yeah, so this is our crude relative risk. Remember we talked about crude and stratum specific back before. This is our crude measure of association, because this is the measure of association when we're just looking at our two variables of interest. So we haven't adjusted for anything, we haven't made any changes, we're just looking at this is the actual association, these are made up numbers, but this is the actual association between drinking and lung cancer in our group, in our sample. Now we're concerned though that smoking might be a confounder, right? Because we're sitting here thinking, we're like, why might this association we be seeing as an association here? So we ask ourselves, could there be something else causing that? And we say, yes, smoking might be the reason. So we first have to ask ourselves our two questions. Are cigarette smokers more likely than non-smokers to drink alcohol? Is our confounder, our potential confounder, associated with our exposure? Then we ask ourselves, are cigarette smokers more likely to get lung cancer? Is our confounder associated with our outcome? Right now, we can probably answer yes to each of those questions. However, we can look at statistically to see if they are. So, we start off to answer the first question. We want to see out of the number of drinkers in each smoking status. So we stratify based on smoking status. So remember, before we were stratifying based on age, or we were stratifying based on gender or race. We stratified based on a lot of things. It just means to separate the two groups. So we have a 2x2 table for our smokers, and we have a 2x2 table for our non-smokers. So now that we have stratified, we can look and say, okay, among the smokers, are people that drink, are the smokers more likely to drink? So we can see that 80% of our smokers drink. Right? So these are all the drinkers. We have 1,000 smokers. So 80% of our smokers drink. When we come look at our non-smokers, we see, oh look, only 30% of our non-smokers are drinking. So this has answered our first question. We now see that smokers are more likely to drink. It's associated with our exposure. Then we want to know, is it associated with the outcome? And that way we can look at the stratum-specific relative risk. So now we can calculate the relative risk for each of our groups. So, actually that's not right. Associated with our outcome, we just want to know if more people with, more smokers are likely to get lung cancer. Sorry. So, are more smokers likely to get lung cancer? So 30 out of 1,000 compared to 30 out of 3,000. Right? I got ahead of myself. Right? So more people in our smoker group have lung cancer compared to our non-smoker group. It's associated with our exposure. It's associated with our outcome. Now, do you think that smoking, the third question, is smoking in the causal pathway between alcohol and lung cancer? That's not a statistical question, that's a biochemical question, I guess? No. Smoking is not. Alcohol doesn't cause you to smoke, which causes you to develop lung cancer, right? It's not in the causal pathway. So we've satisfied our criteria for confounder. Now we want to look at the stratum-specific estimates. So we can calculate the relative risk among smokers. And if you do that, you get a relative risk of 1. And you can calculate the relative risk of non-smokers. And you get a relative risk of 1. So let's look at these two estimates. The stratum-specific relative risk. So remember, the crude relative risk was 1.65. The first thing you want to do is look and say, are my stratum-specific relative risks similar to each other? Because if they're not, we're not going to call it a confounder, we're going to call it an effect modifier. But here, we see a relative risk, a stratified relative risk among smokers of 1, and a stratum-specific relative risk among non-smokers of 1. So the stratum-specific relative risks are similar to each other. So we say, okay, we can buy that. Now you want to know, we'll calculate an adjusted relative risk, but since both the stratums are 1, you know the adjusted relative risk is also going to be 1. And we'll compare our adjusted relative risk back to our crude, yes?
Wait, so if the relative risk for the two stratums are the same, doesn't that mean that, like, what does that mean?
If they're the same, that means we can go ahead and assess for, it means it's not an effect modifier, which we'll talk about in just a second. I'm just telling you because it's a step in the process. But when we're talking about confounders, we just want to stop and say, okay, are these the same? And if they're not, I will tell you what to do about it. But because they are, we're now going to calculate an adjusted relative risk. So we can calculate an adjusted relative risk based on the numbers in our table. An adjusted relative risk simply weights the relative risk based on the strata. So the sigma simply means sum across all groups. Right? Is everybody familiar with the sigma as a mathematical symbol? So you take A times C plus D over the total in the table, and then C times A plus B in the total, and you do that for each table, and you add them all together. So for these smokers, if you had your sheet and could go back because the power would have been on, it's A times C plus D over 1,000. There were 1,000 in the smoking table, right? And then you add that to table 2, the non-smokers. We do the same on the bottom, and we get an adjusted relative risk of 1. So when we're talking about confounding, we're comparing this adjusted relative risk back to the crude. So does anybody remember what the crude relative risk was? 1.65? Now, we ask ourselves, is 1 really different from 1.65? So we say, in general, a general rule of thumb is that if it's about 10% or more different than your crude, you can call it a confounder. You'd say, yes, it is a confounder, and then you would adjust for it. And you would report your adjusted relative risk. So what we see here is that in this situation, once we adjusted, we got an adjusted relative risk that's substantially different from our crude relative risk. And so we say, and we also find out that once you adjust for smoking, which is what we have just done here, once you adjust for smoking, that means you take the variability out that's due to smoking. There's no longer an association between alcohol use and lung cancer.
So if the percent is 10% or more, if there's that much of a difference or more, what do we call it?
Then we say that yes, it's a confounder.
Okay.
We can classify it as a confounder. And then we will report our adjusted relative risk and say that that's really showing the true relationship between our exposure and outcome of interest. Because now we've taken out the variability due to that third variable. Now I want to point out that to be a confounder, it does not have to make the relationship disappear. It has to make the relationship change. So if we had calculated the adjusted relative risk and the adjusted relative risk was 2.5, it would still be considered a confounder because 2.5 is substantially different from 1.65, right? So it doesn't have to make the relationship disappear, it has to make it change. Alright, to minimize confounding, a couple of ways we can do this. We can match for the potential confounding variables. So, if I'm doing a case control study, and I think that age might be a possible confounder, I can make sure that every time I get in a person that's 20, that's a case, I find a control that is also 20 years old. That's matching. The problem with matching is then that you can no longer look at that variable in your analysis. So if it's a variable that you're actually interested in looking at, you don't want to match on it. But if it's a variable that you just think is a confounder and you don't think is interesting to your study, you can match on it.
So if you do matching, you can no longer study that variable?
Correct, because you have essentially taken out any variability that would be due to that variable, because for every person that has it in your control group, you have a person that has it in a case group. Alright, you can also adjust for the confounder during the analysis, which is what we just did. You can use a stratified analysis. There's other ways to do it, but you could do it using a stratified analysis like we just did. You adjust for it after the fact, essentially. So matching happens during the study design period, before you've collected your data. Adjusting happens after the data is collected. You do it mathematically. Or you can restrict your entire study to people who just don't have that confounder measures. So if you think gender might be a confounder, you only study men. Right? You've completely just taken it out of the equation. That's rarely advised unless you have a specific reason for looking at a particular population. Alright, so that's confounding. Now let's talk about effect modification. So confounding happens when the relationship between two variables changes because of a third variable. The variability of a third variable is explaining away the difference between the two. Effect modification means that the exposure-disease relationship is different across levels. So remember when we looked at the stratum-specific levels and I said they needed to be similar? If the stratum-specific levels are different from each other, it means you're probably looking at an effect modifier. An effect modifier is actually a desired thing defined. Confounding, and we don't like it. Confounding is a bias. It is something that's systematically giving you an answer different from the truth. Effect modification, on the other hand, is telling you subpopulations for which your exposure-disease relationship is different. And in epidemiology, we're very interested in identifying subpopulations because that tells us where we can intervene, right? So let's walk through an example. I think it makes it a little bit clearer again. So we have a case control study looking at the relationship between exposure to chemical X and the development of cancer. And we think that gender might be an effect modifier in this relationship. So we have our crude table, our 2x2 table, and we have our crude odds ratio of 21.3. So 21.3 is telling us what? How do we interpret that? It's a case control study.
People who have cancer are 21 more times likely to be exposed to chemical X.
Exactly. Perfect. Exactly. So, but we think that relationship might be different based on gender. Did you guys just like fist bump for that? All right. So we stratify men and women. Sorry. No, you should be proud of yourself. It's excellent.
Thank you.
Great. We can
I
all
just didn't want to.
when we
I didn't want to, show the whole class that we did that.
Sorry. I have a tendency to accidentally embarrass myself and others. It's a character trait or flaw, however you choose to look at it. Regardless, so we've stratified by gender. So we have our table of men and our table of women. And now we calculate our stratum-specific odds ratios. So we calculate odds ratios the same way as a 2x2 table. We've just now separated out our tables, right? So we get a stratified odds ratio. So in men, the relationship between our cancer and our chemical X, we get an odds ratio of 60. But in women, we get an odds ratio of 2. So there's something different about the relationship of chemical X and cancer in men than it is in women, right? It affects the true groups differently. It modifies the effect of the exposure and disease relationship. So when you see that your stratified odds ratios are substantially different from each other, you say, hold up, there's something going on here. I think I have an effect modifier. You stop. You report stratum-specific estimates. You say, okay, wait, there's something going on here. Gender affects these things differently. Gender influences this exposure, disease outcome, or disease relationship. So I'm just going to talk about the exposure-disease relationship among men, and then I'll come back and I'll talk about it among women. But these two groups are obviously very, very different in their exposure-disease outcome, disease relationship. Now, we're not going to go into the statistical tests that actually determine whether or not these two things are statistically significantly different, stratum-specific odds ratios. We're just going to say if they look different, like pretty different, we're going to go with it, okay, for the purposes of this class. Does that sound good? Because if they're different, in an example I give you, they're going to be drastically different. Alright. Let's see. Lost my place. Alright. Final summation. In general, when you're starting, you're going to have an idea. You'll think, okay, I think this variable is a confounder. I think this variable is an effect modifier. But we assess them in using similar steps. We always start, we put our data into a 2x2 table and we calculate our crude measure of association. We calculate our crude odds ratio or our crude risk ratio. You always start there because you want to know what the original estimate is. You stratify by your potential confounder or effect modifier. So whatever third variable you think is having some influence on the relationship between the exposure and outcome, you stratify based on that variable. You then calculate your stratum-specific estimates. You look to see if it's effect modifier. So if your stratum-specific estimates are really different from each other. If they are, you stop. You say it's an effect modifier, and you report the stratum-specific estimates. If the stratum-specific estimates are not different from each other, then you calculate your adjusted measure of association. And you assess for confounding by comparing your adjusted measure back to your crude measure. Does that make sense? We're going to do several little examples to make it clearer. Alright. I have a big, huge pile of papers of fun things to do. I think I gave you the wrong one. Sorry. No, it isn't. I'm just losing my mind. Here we go. Alright, so at the start there's just some more information on bias, which I think is some excellent reading for you to do. Then there is on page, let's see, after the, there should be a page that says bias and observational studies in class exercise. Can you see that? Once you've gotten through the pages are not consecutively numbered. This is the problem.
Page 25 is supposed to.
Yeah, it's page 25. Alright, here's what I want you guys to do. Break up into groups of 6 or so, obviously, if we do that. You guys actually have an individual homework assignment this week. Work all by yourself for your homework. Very excited. Huh? You don't know if you can do that?
I like it.
Feel free to talk to each other, just don't turn in the same assignment, but if you have questions, it's okay to ask each other. It doesn't have to be completely done in isolation, but I'm not going to force you all to turn in one paper of the whole group. Alright. So, but we are going to break into groups for this particular part. So, I want you guys to break into groups. I want you to do all of the exercises in there. So there's a bias and observational studies exercise. There's a bias and epidemiologic research exam sheet thingy. And then there's a confounding exercise. So there's some more reading. And, oh no, I'm sorry. Confounding, you're supposed to answer the questions as you go. Alright? Break up into groups. Come back by 4:15.
like go.
Okay? That sound good? Yes, no, maybe? Because then we're going to walk through all of these exercises together. Yes, no, maybe?